I said a hip hop, the hip me to the hip hop. You don't stop the rocket to the bang bang boogie. Say up jump the boogie to the rhythm of the boogie to beat.
The focus of the last lecture was on splitting fields and on algebraic closures. And this lecture is going to be divided up into two parts. And in the first part, we're going to prove a main result about splitting fields that we stated in the last lecture, but didn't prove yet. So that is corollary 13.4, which says that any two splitting fields for a polynomial f of x in f bracket x over a field f are isomorphic. And the way that we're going to prove this result is to relate it to an earlier discussion we had back in lecture 9. So let's recall, if you have sigma, an isomorphism from f to f prime, an isomorphism of fields, this extends to an isomorphism of polynomial rings, which we'll also call sigma, which goes from f bracket x to f prime bracket x. And we saw that if p of x in f bracket x was an irreducible polynomial, then sigma p of x, which is the polynomial in f prime bracket x that you get by applying sigma to the coefficients of p of x, is irreducible. So what is sigma p of x? It's the polynomial you get from p by taking sigma of each coefficient. Okay, so these two polynomials are both irreducible. They're related by this ring isomorphism. So they're irreducible. That means the ideal that each one of these generates is a prime ideal of the corresponding polynomial ring. And we saw that the quotient of f bracket x by the ideal generated by p of x is isomorphic to the quotient of f prime bracket x by the ideal generated by sigma of p. Okay, so we know something about quotients of polynomial rings by maximal ideals generated by irreducible polynomials. We used this observation and an earlier result to prove theorem 8 in section 13.1 that said if alpha is a root of p of x in some extension of f, and beta is a root of sigma of p of x in some extension of f prime, then there is an isomorphism from f adjoin alpha to f prime adjoin beta that sends alpha to beta. And if you restrict this isomorphism to this subfield of f adjoin alpha isomorphic to f, if you restrict it to this copy of f inside of f adjoin alpha, you exactly get the isomorphism from f to f prime sigma that started this whole thing. So an easy way to remember what this actually says is with this little diagram where you have this isomorphism from f to f prime, and then you have this isomorphism from these larger fields, f adjoin alpha to f prime adjoin beta, where we have an extension here, an extension here. And if you restrict psi down to the bottom, you exactly get this isomorphism sigma. So what are we going to do? Our goal is to prove an analog of this theorem 8, but for splitting fields. These fields, f adjoin alpha, f prime adjoin beta, come from adjoining one root of a polynomial p of x to this field f, or a root of sigma of p to this field f prime. Where do splitting fields come from? They come from adjoining all of the roots of a polynomial. So we'll prove a statement that looks like this one for splitting fields, and this corollary 28 about isomorphisms between splitting fields for the same polynomial will follow directly from it. Remember, the big thing that we're trying to prove is this corollary 28, that any two splitting fields for a polynomial f of x and f bracket x over a field f are isomorphic. And we're going to do it by proving theorem 27, which is a generalization of the result that we just reviewed. So it says, if you have sigma, an isomorphism between two fields, f and f prime, and E is a splitting field for f of x in f bracket x over f, and E prime is a splitting field for sigma of f of x, which is a polynomial in f prime bracket x over f prime, then there is an isomorphism psi from E to E prime such that you take psi, you restrict it down to f inside of E, and you get this original isomorphism sigma. Again, just like for the previous result, you can think of this in terms of a diagram where you have sigma at the bottom from f to f prime. This is this isomorphism. You have another isomorphism between these splitting fields, these extensions, e of f and e prime of f prime, such that if you take psi and you restrict down to the bottom, you get this isomorphism sigma. All right, so how are these two statements related? Corollary 28 follows directly from theorem 27, taking sigma to be the isomorphism given by the identity map from f to itself. So f prime is equal to f and sigma is the identity. So that means that this polynomial f of x and sigma of f of x are the same polynomial. So in that case, what are we saying? E is a splitting field for f of x over f, and e prime is a splitting field for f of x over f also. So these are two splitting fields. And what we're saying is there is an isomorphism from e to e prime such that you restrict to this f inside of e and you get the identity map. So we're going to prove corollary 28 by proving this more general result, theorem 27. And the main idea here is going to be induction on the degree of f. And we're going to use this theorem 8 that we proved earlier. So induction is going to allow us to use this theorem 8. What is the base case of this induction? This is a little clever. We'll do polynomials of degree 1, but more generally, we can do all polynomials f of x together where f of x splits completely into linear factors in f bracket x. Because in that case, what does the splitting field for f of x over f look like? Well, that's some field extension E in which f splits completely into linear factors in E bracket x. So in that case, we just have the splitting field is f itself. Okay, so this is the base case we're going to do. And the first thing that we're going to need to do is talk about factors of f and relate them to factors of sigma of f. So we already saw one case of this earlier, where we said, okay, we have this isomorphism from f to f prime, and this gives a ring isomorphism between these polynomial rings, f bracket x and f prime bracket x. And if p of x in f bracket x is an irreducible polynomial, then sigma of p of x is irreducible in f bracket x as well. So I'm going to pause and erase and just make a more general observation, not just that sigma takes irreducible polynomials to irreducible polynomials, but if you know how f of x factors into a product of irreducibles in f bracket x, you immediately know how sigma of f factors as a product of irreducibles in f prime bracket x as well. We know that this ring isomorphism, sigma, sends irreducible polynomials to irreducible polynomials. But something better is true, that each irreducible polynomial, each irreducible factor of f of x gets mapped to an irreducible factor of sigma of f of x of the same degree. So you can factor f of x into irreducible polynomials. They have some set of degrees, and you apply this ring isomorphism, and you can factor sigma of f into irreducible polynomials, and you get the same number of factors of each degree. There's this correspondence between the factors on each side. Okay, so let's talk about one special case. So if f of x has all of its roots in f, that means it factors completely into products of linear factors in f bracket x. So each linear factor gets sent to a linear factor of sigma of f of x by this ring isomorphism sigma. So sigma of f of x also splits completely in f prime bracket x. So in this case, when all of the roots are already in f or f prime, we see that a splitting field for f is, for this polynomial f of x over f, is the field f itself. And similarly, e prime, this splitting field for f prime of x, is f prime, sorry, for the polynomial sigma of f over f prime is f prime. So the splitting fields are the fields themselves. So in this case, this theorem is true. You just take psi to be the original isomorphism sigma. Okay, so this completes the proof of the base case, which is not just the case where f has degree 1, but the case where f of x splits completely in f bracket x. There's really like not much to prove at all. Psi you just take to be the original isomorphism. All right, so now this is the big induction idea that we're going to assume that the theorem holds for any field f, any isomorphism taking f to f prime, and any polynomial little f of x in f bracket x. Now what we're going to do is take f of x to have degree n, and we're going to take an irreducible factor of f of x of degree at least 2. So that's what p of x is going to be. And how do we know that there is such an irreducible factor of degree 2 or more? Because the case that all of the irreducible factors have degree 1, that's in the base case. So we don't need to prove anything else in that case. So we're going to name one particular irreducible factor of f of x of degree at least 2. And we know that we have this factor of degree at least 2, irreducible factor of f of x. There's a corresponding irreducible factor of sigma of f of x, and it is sigma of p of x. It's the corresponding irreducible factor of sigma of f of x. So it's this irreducible factor that has the same degree as the degree of p of x. Okay, so we're going to use these irreducible factors, one of f and one of sigma of f, to get to a point where we can apply this induction hypothesis. So I'll pause and erase and explain that big idea. First, I want to say that there is something missing from this induction hypothesis here that's really important. That we want to assume that this theorem holds for any f, any isomorphism sigma from f to f prime, and any polynomial f of x and f bracket x of degree less than n. So that was the part that I didn't write in on the previous board. So now what's the idea? We have this polynomial of degree n, one more than the place where we can apply this induction hypothesis. And we have an irreducible factor of degree at least 2 and a corresponding irreducible factor of sigma of f of the same degree. So the idea is in a splitting field for f, it contains all of the roots of, in a splitting field for this polynomial f of x in f bracket x, this splitting field contains all of the roots of this polynomial f of x, and we know a splitting field exists. So in particular, it has to contain a root of this irreducible factor, p of x. So let's name one. Let's say alpha in E is a root of p of x. And okay, in a splitting field for sigma of f, we have a corresponding root of this irreducible factor, sigma of p. So we're going to name that beta. Beta in E prime is going to be a root of sigma of p of x. And the idea is to apply theorem 8 now to f adjoin alpha and f adjoin beta. That theorem 8 says that there exists an isomorphism psi from f adjoin alpha to, f prime adjoin beta, such that psi restricted to f is this original isomorphism sigma. So here's this diagram to remember what this really is saying, that psi is an isomorphism from f adjoin alpha to f prime adjoin beta. And you restrict down to this copy of f inside of f adjoin alpha, and you get this isomorphism sigma from f to f prime. So the important thing is, where do alpha and beta come from? They are a root of this irreducible factor p of x of degree at least 2, and the corresponding irreducible factor sigma of p of sigma of f. Okay, so how are we going to apply the induction hypothesis? We're going to apply it not with f and f prime, but to f1, which we're going to set equal to f adjoin alpha, and f1 prime, which we're going to set equal to f adjoin beta. And with f1 and f1 prime, just with that new notation, what is psi? It's an isomorphism from f1 to f1 prime. So yeah, so now we have a field f1 and an isomorphism, which we're calling psi, from f1 to f1 prime. So what's the polynomial that we're going to work with in f1 bracket x of degree less than n? Well, how does f of x factor in f1 bracket x? We have this root alpha, so we get a linear factor. We have x minus alpha times something of degree n minus 1 that we'll call f1 of x. Similarly, how does sigma of f factor in f1 prime bracket x? Well, we have a root beta, so we have this linear factor. So we get x minus beta times f1 prime bracket x. Sorry, f1 prime of x. This is a polynomial. And the important thing is that the degree of f1 is n minus 1, and the degree of f1 prime is also n minus 1. Okay, so now this is starting to look better. We have this field f1. We have an isomorphism from f1 to f1 prime. And we have this polynomial f1 in f1 bracket x of degree n minus 1, which is less than n. So what does this say? This says assume the theorem holds. And what is the theorem about? It's about an isomorphism between splitting fields. So where do we find a splitting field for the polynomial f1 of x over this field f1? And the key observation is that E, this splitting field for f of x over f, is a splitting field for f1 of x over f1. So what does that mean? That means that f1 of x factors completely into a product of linear factors in E bracket x, and there's no proper subfield of E over which f1 of x factors completely into a product of linear factors. So why does it have these properties? Well, E contains all of the roots of f, and f1 is a factor of f. So certainly E contains all of the roots of f1 of x. So f1 of x factors completely into a product of linear factors in E bracket x. That's true. How do we know it's actually a splitting field, though? We need to show that there's no proper subfield of E over which f1 of x factors completely into a product of linear factors. Well, okay, I mean, suppose there were. If there were a proper subfield of E that contained f1 and all of the roots of f1 of x, then because f1 contains f, and f1 contains this first root alpha, which is the one root of f that we don't know is also a root of f1, then this proper subfield would contain f and would also contain all of the roots of f of x. So it would be a field over which f of x split completely into product of linear factors. So this would be a contradiction if there was a proper subfield of E over which f of x split completely into a product of linear factors. And because we started by saying E was a splitting field of f, this is a contradiction. Okay, so what have we seen? We've seen that E is a splitting field for f1 of x over f1. And the exact same observations tell us that E prime is a splitting field for f1 prime over the polynomial f1 prime of x over this field f1 prime. So now saying assume the theorem holds, we can apply this result. And that tells us that E is isomorphic to E prime, and in fact tells us a little more. So we know that E is a splitting field for the polynomial f1 of x over this field f1. For the same reason, E prime is a splitting field for the polynomial f1 prime of x over f1 prime. And f1 and f1 prime are polynomials of degree less than n. So we can apply this induction hypothesis, which says that there is an isomorphism. I just need another letter, so I'll go with eta from E to E prime, such that you restrict to f1, and you get this isomorphism psi from f1 to f1 prime. Earlier, where did this psi come from? This came from applying theorem 8, and we know that psi restricted to this f is sigma. So E is an extension of f1, which is an extension of f. So we can restrict to a copy of f inside of E. F is a subfield of E, and see what is eta restricted to f. Well, it's the same as psi restricted to f, and that just is sigma. So this completes the proof of this theorem. I find it helpful to look at this diagram. We have this eta at the top, this isomorphism between these splitting fields. We have this intermediate level, which came from applying theorem 8, adjoining one root of this polynomial f of x and one root of this polynomial sigma of f of x, and then the bottom isomorphism sigma down here. Okay, so this argument was a little complicated, but the main thing that we wanted to do was argue by induction on the degree. It's important to remember what the base case is, that it's not just the degree being 1, but the case where your polynomial f of x splits completely into a product of linear factors already in f bracket x. And then we want to apply this theorem 8 to find this intermediate field, f adjoin alpha and f prime adjoin beta, and use this intermediate field to get a polynomial where we can apply the induction hypothesis. Okay, so I want to point out that what I've presented here is the argument that's in Dummett and Foote, but using some of the ideas from earlier about homomorphisms on polynomial coefficients from Conrad's notes on splitting fields. Conrad gives a different proof of this theorem in this notes on splitting fields. He proves the analog of this theorem 8 and theorem 27 together. So it's one longer argument. And it's not quite the same because in these notes, something stronger is proven. It doesn't just say that there is an isomorphism between these splitting fields where you restrict down to the bottom field f and you get the original isomorphism sigma, but it says something about the number of different isomorphisms you could have between E and E prime. So that's not something I'll talk about now. There's also a further discussion in these notes about what if you make some extra assumptions on your fields or polynomials, like how this is related to the notion of separability that we'll talk about in the next lecture.